All right, welcome to our session, I think it's session 3 now, of Introduction to Machine Learning, the first part of a 2-part series. In this first part, we're going very broad and we're focusing on algorithms and the approach to training a machine learning model. How do you build and train a machine learning model? And then in the second part of this course, we'll do ML metrics and evaluations. How do we determine the performance of it? Today in session 3, we just finished going through assignment 1 and overview of assignment 2. And for the knowledge and concepts we need to apply to that, particularly to assignment 2, we're going to focus on building a machine learning model. And the way that we're going to learn about how to build a machine learning model is through a package called sklearn. So we're going to focus on modeling methodology. What are all the step-by-step things that we need to do? We're going to start with a very simple, straightforward process, and then we're going to build and expand on that over time throughout the course in order to train very, very well-performant models that generalize to data sets beyond our training data set. Before we dive into logistic regression, I think it's important that we take just one quick step back to talk about probability, since all of these models are probability based, and make sure that we have a reference in probability for us to talk to and to speak about as we move on to these models and algorithms. In the last part of this, we're going to talk about logistic regression. So now we're introducing our second machine learning algorithm. We talked about linear regression last time. We're going to build on that linear regression formula. We're going to do a really cool transformation to it, and we're going to turn it into a whole different algorithm, logistic regression, which is a really important foundational piece to neural networks. So we're starting to get there. At the end, we'll pause the recording, and we're going to talk about a discussion question, thoughts, stance, AI education, particularly grade school. Okay, let's do a quick introduction to machine learning models, particularly sklearn. What is sklearn? sklearn or scikit-learn is an open source Python library that provides a very simple and efficient tool for manipulating your data and applying machine learning algorithms. What's great about this is we don't have to reinvent the wheel. We don't have to go through and write by hand how a decision tree works, how a random forest works. Imagine if we had to do that. And the other great thing is by leveraging these packages, we get a really consistent way of these things being implemented across developers. So your way of implementing your random forest is the same way as of my implementing my random forest. It's quite useful to do that. It's built on top of a lot of other key Python libraries. We have NumPy, SciPy, Matplotlib. So all these things really work together. There's a lot within sklearn, and we're going to start to explore it a little bit at a time. One really useful thing is just the algorithms, the linear regression algorithm, the logistic regression algorithm, the random forest algorithm. But in addition to that, sklearn also provides us with tools for prepping and processing our data. How do we fill null values in our data? How do we scale this information so that they're all on the same level of ordinality? How do we encode our categorical data? How do we transform it from string labels into numbers that the machine understands? sklearn offers all the tools for us to do that, so we don't have to do it by hand. And then they also offer model validation tools as well. So how do we calculate accuracy, precision, and recall? And how do we bake all of this into like a pipeline that's really smooth for testing and iterating over different models? That's cross-validation. So we're going to explore some of that. In sklearn, at a really simple level, here are the steps in any machine learning, in any data science project. Here are the steps we're going to go through. We're going to import some libraries. That's important. We got to import them to use them. We're going to load our data. Then we're going to split our data into training sets and test sets. For your assignment, this piece is optional because we're going to talk about this more as we go. Like I said, we're going to build on it. So initially, maybe for some of these data sets, we're not splitting the data and we're just going to train and evaluate on the same data set. Bear with me through that. As we evolve over time, eventually we'll split the data. So import your libraries, load your data, split your data. Then you're going to choose an algorithm and train a model over it. We're starting to understand that which algorithms are applicable to which classes of problems. We know that linear regression is applicable to problems with scalar data, where the target variable, the y variable that we're trying to predict, is scalar. It ranges from on a set of values of numbers that aren't discrete categories. And then finally, we want to evaluate our model. We want to see how well it's doing. So these are the steps that we're going to go through. Let's walk through an example. I think it's easier if we just look at the code. Here is our sklearn example. Let me see what this looks like on your guys'. A little more zoom would be good, huh? Okay. All right, here's an example that we designed to practice sklearn for linear regression. We're going to focus on a housing data set for this. So this is if we have a housing data set with historical sales prices, that means it's two things. One, it's a supervised learning problem because we have the answers. We're asking a model to predict what a house has sold for, and we know what a house has sold for. We have the y variable, the target variable we're trying to predict. The second piece is that it is a regression problem because it's a scalar value that we're working with for our target variable. So we're going to follow these steps. Our goal is to train, evaluate, and interpret our linear regression model. We're going to import these libraries for now. And we need to load this California housing data set. Let me see if that just got stored into our, nope, one moment. I may need to, I think I'm missing a cell in here, which is unfortunate because it means you guys are missing that in your assignment. We can't just import housing. We have to actually load this. I think we were just missing one line here. Yep. All right. I'll drop this in the Slack channel and update the repo, but it already created the assignments for you guys, so it won't automatically update. So you have to add a line into your assignment. Or this isn't the assignment. I'm sorry. This is our work through. That's all right. So housing, fetch California housing. What's great about sklearn and pandas and some of these other packages is they actually have data sets, toy data sets, built into the packages, that file structure I was showing you at the beginning of class, that we can actually just load without us even having to drop into this folder here and upload the data into a location our machine can find it. We can actually import from sklearn.datasets, import fetch California housing data set. And I can set this variable housing equal to this function call, fetch California housing data set. And what that's going to do is it's actually going to grab the California housing data set from the sklearn package, which is kind of nice. We can look at what's in here. We can see that there's some data, there's a target. Does anybody know what type of Python data type this is? We've got keys and we've got values. Which Python data type has key value pairs? Oh, and if there's chat, sorry. Oh, no, that's just about the door code. All right, let's see. We can probably find out if we do a type on housing. We run type housing. Oh, it's going to give you a complicated answer. But this looks to us like a dictionary. So the key value pairs, it looks like a dictionary, so we can probably parse this like a dictionary. Here we have data and we have target. Which of these is our Y variable? Okay, target is going to be our Y variable that we're looking for, and data is going to be our X variable. So when we say Y equals MX plus B, from a data science nomenclature perspective, a target variable is equivalent with our Y. All right, so let's see if I put this into a data frame. So we have, under data, we have this array of information, but I don't know what any of this means. It's actually just numbers. However, we have a thing here called target names and feature names. And we can see that target name is median house val, and feature names, oh look, here's all the names for our columns. Great. This is really useful key value pair information, but how do we put all this together into a pandas data frame in a way that's a little easier for us to parse? So here we have feature names. We can do that by calling pd.dataframe. PD is the pandas package, and data frame is how we create a data frame here. And to this, we're going to pass housing.data and the housing.feature names. And here is our X training data set. So now we have median income, house age, average rooms, population, longitude, latitude. Fun fact about the California housing data set. This was created because there used to be a different data set that was a very popular introduction to data science and machine learning data set called the Boston housing data set. You may hear about that one as you're reading through material online. That one had some ethical concerns. People were concerned about the ways that these models were predicting house prices based on things like zip code. And they thought it was biased and not representative and really not fair in many ways. And so for that reason, they created this different data set called the California housing data set. And in the California housing data set, they took blocks of houses and assign them median income, house age, average room. So this is really, this like record here doesn't actually represent one house. That's why you can see 6.9 rooms. How can you have 6.9 rooms? You can have 6 rooms or 7 rooms, but not 6.9. The reason that's there is this is really an average across a set of houses in an area. So they did this to deal with some of like the ethical concerns of the other data set. So if you're curious, average, that's why it says average occupation, population, etc.
I have a quick question.
Yeah.
When you do PD, it's just the pandas is basically a different way of viewing the data instead of like, okay, because I thought pandas was a completely whole different like coding type thing.
Yeah, pandas, a different coding thing from sklearn. Is that what you were asking?
Yeah, so it's just the way that it pops up, or is it completely different?
That's a good question. Pandas is a package that has its own data type. So just like we have integers are data types, floats are data types, strings are data types, pandas invented this data type called a data frame. And it's its own data type, and it's designed to hold tabular data like this. Tabular data that's in this structure and format. So one advantage is, yes, it looks pretty. Honestly, it's easier to look and read this than it is to look and read this. This is kind of hard for me to parse as a human. So it is more friendly, but it offers more than that, is what I'll say. If you have something that is a pandas data frame, you can apply manipulations, transformations to that in a way that is easier than if you had it in some like base formats, such as everything was a list of lists. We could also represent this data set as a list of lists, but then we wouldn't get all the friendly, nice, cool functions that come along with being a pandas data frame. I don't know if I answered that well. Okay. I think you guys will see. Also, I have another typo here. There's a lot of typos in this thing. So when you make a pandas data frame, what I did here is I said pd.dataframe, and I gave it some information and it output this data frame, and it looks like it saved it into an object. But in reality, this didn't get saved anywhere because I don't have an assignment operator here. So don't forget to assign that to something. And then you can call df afterwards if you actually want to show it.
I wonder why they call it a data frame and not a table.
That's a good question. I don't know the answer to how the word data frame, got popular. It's a good question. Now I'm curious. If anybody looks it up and knows, let me know. Drop it in the private chat or in the Slack channel. So if we want to look at a particular column in Pandas, we can say df at square brackets and then the name of the column. So here we're saying df at median income. Oh, I've got this in multiple places. Okay. This needed a little, I must have been doing something in there from last class. Next, we want to set our Y target variable. So to the DF, to the data frame, we might want to add like price, for example, something for us to predict. And actually, I should be using the name that we're going to keep going with price. I should have used the name that they said in there. But so now we can look at our full data set, and we have our X and our Y variables. So here, all of our X variables, median income, latitude, longitude, etc., and Y is our price variable. If you have your data all together in one data set like this, I know it's weird because we had them separate and then I combine them and then we're going to split them apart. Again, you don't have to do that. I'm just showing you how to split your data set apart in case you guys are working with data sets for which they are combined, which you will for your assignments. We're going to split into X and Y. So we want to train our regression formula. So we have to have an X data set of X features and a Y data set, the target variable that we're trying to predict. So X, we're going to use the syntax df.drop, and we're going to drop the price column. This is fine. I would actually maybe even swap these in order. And then for Y, we're going to define that as Y at price. Remember I said you can do train test split for bonus credit, bonus points. This is us applying train test split. We'll talk more about this another time, but essentially we're going to get 4 data sets. We're going to get an X test, an X train, a Y test, and a Y train. So we're going to get an X and a Y data set for training our model. And we're going to get an X and a Y data set for evaluating our model, for telling how well our model actually did, so that the data that we're using to train the model is not the same data we're using to evaluate the model. But for now, we're just going to move on with just the X. The X data, and here's our Y data, if we wanted to take a look at that. So here's our X data set, our X features, and our Y data set. And here we're going to train a linear regression model. So we're going to say model equals linear regression, which is what we imported from sklearn at the top of the file. And to fit this model, to train this model, It's a very simple line of code. We're just going to call model.fit. We're going to pass in our X train and our Y train. So our X and our Y variables, in this case, relative to our training set that we've set aside. So X train and Y train. When we fit the model, what is actually happening is sklearn is going through that algorithm that we talked about to find those coefficients, to find those best weights in order to predict that Y outcome for these models. So it's going through that mean squared error, minimizing the loss of the residuals that we looked at, minimizing that error, and figuring out which weights applied to these columns minimizes the error. That's what the fit function is actually doing. Now we're going to call, I don't know if I actually ran that. Here we are. And now we have a model. So we have a fit model. Fit means trained. We have a trained model. And this is now you've trained your first machine learning model. Congratulations. And now we want to actually use it to make predictions. We want to see how well it does at predicting. So we can call model.predict, and we can pass it an X data set. Notice that we are not passing it a Y data set. We are asking it to make Y predictions based on X data. So we're asking it, hey, here's a bunch of houses. Here are some elements and some features about them. What do you think, based on your weights that you've trained, your expert system, what do you think the price of these should be? We're asking it that question. And that's what YPred is. And then it gives us a series of predictions here. So it'll say, for house 1, here's what I'm predicting. For house 2, here's what I'm predicting. For house 3, here's what I'm predicting. Now we actually know the answers. We have the answer key here. We have Y test. So we know what the answer for these houses are. We know that the answer for house 1 is this. The answer for house 2 is this. The answer for house 3 is this. So we can actually evaluate the model's performance. We can calculate the mean squared error, the MSE, and the R-squared values by calling MSE. It's one of the packages we imported at the top, the mean squared error. And we pass Y test and YPred. So we pass 2 Y's to our M squared. We pass it what the model thought the answers were, what it guessed, what it predicted the answers were based on its trained weights, and then what the ground truth answers were in reality. And then the mean squared error will calculate the difference between those and give us a metric, which we'll learn more about these metrics in the next course. So you don't have to know too much about, I wouldn't worry about the details of this, but just the overall process. The fact that we pass a Y test and a YPred, so a Y true and a YPred, what our model predicted, to these scoring functions to score the performance of a model. And then at the end of the day, we have a formula. We have Y hat equals beta sub naught plus beta sub 1 plus etc. So how do we figure that out? Let's do this. So we want to figure out what our formula is. You guys have to do this for assignment 2. I believe assignment 2, assignment 2. If we call model.intercept, we can get -37. What does this represent in this formula? What does the -37 represent in this Y hat equals beta sub naught plus beta sub 1 times X plus etc.?
So the sum of the squared numbers, I forget the technical terms there. But.
That is, the sum of the squared error. That is a good question. I don't have the sum of the squared error here. We could do that. I'd have to look up what that package is. The intercept is not the sum of the squared errors.
Would it be the beta sub naught?
There we are. It's the beta sub naught. So this, I have it B0 because I can't do subscripts here, but it's the beta sub naught. So as we're starting to build our formula here, negative 37 is our y equals mx plus b. Negative 37 is that b. It's the intercept in that formula. So now we can build our formula, y equals negative 37. We can also get the coefficients. Remember I said they're the coefficients, they're the weights, they're the parameters of the model, or the different words. In this case, in the sklearn package, it's called coef, which stands for coefficient. You do have to put an underscore afterwards. If you call model.coef, this is how you get your model coefficients. So this is the, here we have 4.4, and notice it's e to the negative 1 here. Sometimes when we have really long numbers in Python code and in sklearn and pandas, it'll put it in scientific notation. So if you remember from scientific notation, -1, you have to move that decimal over one place. So it's actually, I don't know why I put 0.04 here. It's 0.4 for that median income. And so if we can start to build this formula now. We can map these. This is just an array of numbers, but how do we know which of these columns it matches to? It's in the order that we passed it. So it will progress median income, house age, average rooms, average bedrooms, population. So the weight applied to median income is there. The weight applied to house age is here. The weight applied to average age is here. Which of these weights is the smallest? Which of these coefficients are the smallest? You can just say the first, second, third, fourth. Like this is first, second, third, fourth.
Wouldn't it be the last one on the list?
It looks like it would be the last one, but this is to the -1, which means this is
Oh, so
4.
first one, second row.
First one, second row. Here we are. So this is a confusing way to read this, and I should probably just try to print it out in a more readable format. But the scientific notation's a little confusing. But this is -6 means we'd actually have to move this decimal over like 6 places. So this is effectively 0. So this is, according to the model, if all of our features were on the same scale, which we're going to talk later about what that means, but for now, just accept that. If all of our features are on the same scale, this feature would mean the least. It would be the least informative to your linear regression model. So let's see, that is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Population. Doesn't care about population. Now, that's not necessarily how we can interpret that right now because we didn't scale our features. What do I mean by that? If you have number of bedrooms, and that's, that ranges, you could have 1, 2, 3, 4, 5, 6. There's probably not a ton of houses with 15 bedrooms, with 20 bedrooms. We're getting to like a small population there. So your range of bedrooms might be 0 to 20. And if we look at something like square footage, your range is much larger. So the number that your model multiplies square footage by for your outcome is going to be very different than the number your model multiplies number of bedrooms by. For example, you add a bedroom, maybe that's worth another $10,000. You add 1 square foot, that is certainly not worth $10,000. So if we want to have these coefficients on some interpretable scale where we can all understand bedrooms is worth more to the model than square footage, we need to do something called scale them. That means all of our features have the same range. We're not changing the numbers or the order of the numbers. We talk about this more in this class, but I'm introducing this concept now. That means we apply sklearn packages and approaches to put everything on the same level. So everything would range between 0 and 1. Bedrooms would range between 0 and 1. Square footage would range between 0 and 1. We can apply math to condense those values down to the range of 0 and 1 without changing the order in which they occur in the data set. And that would enable us to actually say one is greater than the other. And then we could say the coefficient that was the largest had the biggest impact. But what you need to know here, what you need to take away from your assignment is how do you take these coefficients, map them to these feature names, and be able to write out a formula like this. So here's our y equals beta sub naught plus beta sub 1 plus beta sub 2. So we have y equals negative 37 plus 0.4 times median income plus essentially 0 times house age. Guess it doesn't matter. Plus 0.01 times, I actually think it's 0.1, sorry. Plus, this is actually a negative value, negative 0.1 times average rooms plus 0.7 times average bedrooms, etc. And then if you actually, I'm gonna fix this on, sorry. If you actually gave me a record, a new record, this is the way that inference works in this machine. You gave me a new record and you said, predict the house price for this. I don't know what the house price is. And you told me something like the average, you told me the median income was 8.32. You told me that the house age was 41. You told me the average rooms was 6.9. You told me that the average bedrooms was 1.02. You can start to see how I can just plug those numbers into this formula that we created. And if I ran and evaluated that, I would get a y value. I would get a single value prediction for y here. If I took negative 37 plus 0.4 times 8.3252 plus 0 times 41, we would just evaluate the equation to get an output. That's our model's prediction. We compare that to what happened in reality, and that's how we know how the model would perform on that given record. Let me pause here. Any questions on this? Okay. We're going to take a break here. And I would like you guys to, let me see if this is linear regression. Yep, evaluate the model. Okay. I would like you guys to try this out. I would like you guys to try to work through this same thing in the sklearn breakout notebook. I will drop the link to this notebook in the Slack channel. We're going to combine, sometimes we combine our breakout and our break together. We're going to do that again here. I'm going to give you guys at least 15 minutes, come back at 7:30, and then we'll at least check in and see how things are going. So break and breakout combined, 7:30. we just had this whole discussion on creating agents with using large language models. You guys should come in person because sometimes we chat on the breaks. But oh man, my screen, just this thing does that. I'm not supposed to. I'm finicky. I'm not supposed to touch my computer once. What do you guys see? I don't see anything. I have to reshare. But Microsoft Copilot agents, pretty interesting. Check out RAG architecture. If you guys haven't already, it's like a year old now, but it's a good starting place for how do you constrain the output of a large language model. Our example is, what if you don't want it to opine on things like how far is it to the moon, and you only want it to answer questions relevant to the domain you're interested in, maybe relevant to your company or relevant to your organization, and not answer questions that are outside of a knowledge domain. You can essentially use RAG. Microsoft has made that very easy with Microsoft Copilot agents. Okay, let me share my screen because my this TV is finicky. So sometimes if I bump the wrong thing, it stops sharing. I want to check in how we're doing here. Working with sklearn. Nope, I'm in the wrong thing. Breakout. Okay, our breakout exercise here. We're going to use sklearn on the diabetes data set. So here from sklearn.datasets, we're going to import load diabetes. Here we have diabetes as load diabetes. We're going to create a pandas data frame, and we're going to pass it diabetes.data, which is one of those key value pairs. We're going to pass it diabetes.feature names to name our columns so they don't come across with no names. And we're going to create another column called progression on that data frame. And progression's really our target variable, and we're going to call it diabetes, or we're going to use the diabetes.target data to define that. So let's run that. And let's actually just look at the whole data frame. I don't know why we're not doing that here. So let's check it out. And there we are. And you know what? Actually, let me download this. I don't want to be doing work in here because I use this whole drive class to class. So let me just download. I think I have to zoom out here. One moment. And let me just drop this into our example folder here where I can. I might have to restart this, so give me just a minute. Okay. And let me turn, I have too many notebooks open. All right, so here's our entire data frame. And once this loads, we can see we have some features associated. And you guys can read the documentation and read that page I linked to learn what these features are. And then we have some information about a patient, and then we have their progression along the disease. What type of problem is this? Is this a supervised or unsupervised learning problem?
I would say that it seems supervised.
This is a supervised learning problem because we have patients and we know what their disease progression was. So we have answers essentially to what happened, to what the outcome was. We have something called the target variable. Is this what type of problem is this in terms of, is this a regression or classification problem?
regression.
This is a regression problem because we have scalar values. I know we haven't learned about classification problems, but we will. So this is a regression problem. The first thing we're going to do is split the data into training and test set. So we have 80% of the data set aside for training and 20% set aside for test. I'm just going to do this. Here we are. So we have X-train, X-test, Y-train, Y-test. I'm doing this part. I'm going to ask you guys about the next sections, but this part was extra credit. So I'm just going to do this and we're going to move on. We're going to call an sklearn function called train test split. And we're going to pass it our X and Y. I actually prefer syntactically to break this apart because it's a little unclear. It just gets, the code gets very convoluted. So I prefer to say X is equal to df.drop progression, Y is equal to df.progression. Just by nomenclature, X is typically capitalized if it's more than one column. If we have a series of columns, X is capitalized. Y is lowercase because it is one column, essentially. Then you want to set how. So I'm going to train test split. I'm going to pass it X. I'm going to pass it Y. And then we're going to say how big we want that sample size to be. So 20% of our data, we're going to set aside into a test set that we're going to put under lock and key and not use. Random state, we're going to set equal to 42. What random state is basically a random seed. It tells our program, do things randomly, but in a way that every time you run a sample on it, it executes the exact same output. So if you were to rerun my code, it would put the exact same people into the test set as it would put on your code on your machine. So it is random, but it's reproducible random. It runs the same way every single time. Fun fact, I would encourage you to look up, why do we use the random state equals 42? Why do a lot of people use that? You can use whatever number you want. It does not have to be 42. It can be anything. But if you will see 42 used a lot, and it's kind of a fun rabbit hole. So we're going to run that. Next, how would you guys initialize and train the linear regression model? Does anybody have some code that they're willing to share either in the chat or in the Slack channel? All right, let's go look what we did for our other notebook. Let's keep scrolling here. All right, here we trained a linear regression model. You think we can just copy and paste this code? Yeah, probably. So model, we're going to define that as linear regression. We're not going to pass any parameters to it, so we're just going to use the default assumptions from the package. And then we're going to call model.fit. We're going to pass X-train, and we're going to pass Y-train, and we're going to run this. All right, how do we make predictions with this model?
Model equals linear regression.
Say that again.
So model equals linear regression.
Linear. So we have our model equals linear regression.
Oh,
I think you were answering the question before. You're good. We fit this model and we trained it. How can we use model to make predictions? So we have model, and we have to, well, this thing, we're going to call a function called .predict, and to predict, it's a function here, and we have to pass a data set. We have to ask it to make a prediction on a data set. So in this case, we trained it on XTrain, so we should probably ask it to make predictions on XTest. And if we do it this way, we can see what the predictions are. But we probably want to save those predictions back to a variable. So save it back to ypred. All right, did anybody get to calculate and print the mean squared error and the RMSE? Let's go see how we did that in here. So we had our sklearn breakout. Sorry, our example here. We made predictions, so we had model.predict, and then we had our ypred, we had our ytest, and let's see if we can just copy this. All right, let's go ahead and make predictions. I feel like I'm in the wrong notebook here. Sorry. I was. All right, MSE equals our mean squared error, ytest, ypred. The R squared we're going to call this R squared function from sklearn. We're going to pass ytest and ypred. Why are we passing ytest and ypred?
I mean, we just put ypred into the predict for the XTest, and we haven't used the ytest yet. And since we're calling XTest and now we're comparing it with the ytest, that seems like the logical choice for me.
That's exactly it. So we're comparing ypred, which is what our model predicted, versus our ground truth answers. This is like an exam. We're giving what's the answers that the machine put on the test, and then we have the answer key here with ytest. And we're using these two methods, two different methods, mean squared error and R squared, to calculate the performance, how well it did on that test. So here's our metrics here. So some questions for you guys. We're going to keep moving with class because I know we only have an hour and 15 and we haven't really opened up too much of the slides yet. Is how well did the model perform based on MSE and root mean squared error? What did the coefficients tell you about the relationship between the features and the target? And are there any improvements that you would make on the model? We'll maybe come back to that if we have time, but I don't know that we will today. So we're going to keep going. Let me see how long our probability content is here. We may just jump to logistic regression. We are. All right, let's talk about logistic regression. We're going to skip over our probability content. Okay. Great. Let's talk about our second algorithm, logistic regression. And this is our first algorithm that we're introducing for classification problems. Up until this point, everything we've done has been regression. We've been talking about scalar outputs, but what do we do when we have a problem that we can fit into discrete bins into discrete classes? So if we think about, if we think about apples, bananas, pears, those are 3 classes. That's a 3-class problem. You could put it on, 1, 2, or 3, but for many reasons, which I think we'll discover, it makes more sense to map that type of problem to a classification problem. And the way that we're going to learn about classification problems is through our second algorithm here, logistic regression. Let's start with this problem statement here. We're actually going to use the diabetes example, but instead of being a numerical output, we're going to think about it as 1 or 0. They're either at risk for diabetes or they're not at risk for diabetes. So the problem statement here is you're a healthcare provider, or a healthcare provider wants you to predict whether a patient is either at risk for developing diabetes or they're not at risk for developing diabetes. And this is based on their BMI, based on their blood pressure, based on their glucose levels. And you wanna classify patients into 2 categories: those who are at risk, which is a 1, and those who are not at risk, which is a 0. What you're going to use to do that is logistic regression. And this model is a statistical implementation used for binary classification. And we can leverage it to predict the probability of an outcome that belongs to one of 2 categories. So unlike linear regression predicts a numerical output, which we can quantify on a scalar. Logistic regression predicts a probability of an event occurring. And the output is always between 0 and 1. So it predicts a probability of 0.1 or probability of 0.2, probability of 0.3. So what is the likelihood that you are at risk for diabetes? Eventually, we categorize these into 0 and 1. But the outcome for logistic regression is always on a range between 0 and 1, so decimal points between 0 and 1. There's going to be a lot of applications that we talk about and walk through here. One is predicting whether an email is spam or not, or predicting whether a customer will make a purchase or not. In your own companies and organizations, you might have something called a churn model. You might have a model that tries to predict, is a customer going to leave our company within the next X months or within the next time frame. You could apply a logistic regression to that to predict, are they going to leave or are they not going to leave? So why not linear regression? I mean, if essentially everything we could just transform into linear regression, right? We could take apples, bananas, pears. We could say apples are 1, bananas are 2, and pears are 3. And then couldn't we just build a linear regression model to predict 1, 2, or 3? Well, linear regression predicts continuous values. So they can range from negative infinity to positive infinity. If our linear regression model predicts a 4 for our 1, 2, 3 of apples, bananas, pears, what do we do with that? What do we do with a 4? It doesn't really make sense. The concept that we're trying to apply doesn't make sense for linear regression. And what if it predicts 1.5? Well, is that an apple or is that a banana? So there's a lot of questions that arise, and that's where constraining things to this binary outcome, to this 0, 1 through logistic regression, could be a more fitting application when you're looking at problems that are made up of distinctive classes that we're trying to predict. So the other really big advantage that, and I can't underestimate this one enough, the other really big advantage that logistic regression brings that linear regression does not to multi-class problems is probability. This probability served, or this likelihood of something occurring. So we can say, what is the probability that this person is at risk for diabetes? Is it a high probability? Is it 0.99? Is it 0.98? That's a really high probability based on this model's decision method. Or is it 0.5? Is it maybe less certain? How certain is the model about its classification into this class of one class over another? So the probabilities offered by logistic regression is a huge advantage for classification problems, and why you should apply logistic regression to these types of problems instead of linear regression. We'll talk about decision boundary here in just a little bit, but the other advantage is with that level of confidence. If we can look at the model's output probability and say, for some people it's 0.5, for other people it's 0.6, for other people it's 0.7, we can decide where we want that decision boundary to be. Default is 0.5, so by default, everybody who's above a probability of 0.5 is of the yes class, is of the predicted maybe at risk for diabetes class, and everybody that's below 0.5 is of the not predicted at risk for diabetes. But that threshold, that decision boundary, we can actually move. We have control over where we set that, and that gives us a lot of control in how our model makes its decisions in logistic regression. I hope I've motivated this enough. Let's look at the formula. This part I find very interesting because here we are going to take a linear regression formula. Here we are going to take a linear regression formula. We're going to do something fancy to it, and then it becomes logistic regression. So in this case, the model is going to use the sigmoid function to transform the output of our linear equation into a probability. So the formula here is 1 over 1 plus e to the negative, and then there's our formula. I'm going to draw on this. I only have a trackpad, so forgive me here. The formula is 1 over 1 plus e is a mathematical number. You guys remember that? So it just like pi, it represents an actual number. Like pi is 3.14. E actually represents a number. So 1 over 1 plus e. And then we have our formula here. I'm going to call it I'll call it formula. I can't type on here. This is really hard on a track. Form. 1 over form. This right here is our y equals mx plus b. We don't have to, well, y is over here. So y equals 1 over 1 plus e to the negative, and then this is our mx plus b. So this is our mx plus b. Or, as you see in this formula here, beta sub naught plus beta sub 1 times x. And remember, this is just one feature here, but you can imagine that if we were to expand that formula, that's one feature. You can imagine if we were to expand this formula inside of that parentheses, you could also do beta sub 2 x all the way up to beta sub n. Beta sub 2, x sub 2, all the way up to beta sub n, x sub n. So logistic regression is just a mathematical transformation on top of the linear regression formula, that base formula that you guys have already learned. So if we have house prices and we're trying to predict something with a house, will this house sell within 30 days? Yes or no? We could put all of those features into the expression of this formula. Let me pause for just a moment. Does this make sense to you guys? Okay. When I first learned about this, I thought it was really clever and very cool that logistic regression was a transformation on our linear regression, that you can actually see the formula for linear regression in logistic regression. And later we'll learn how logistic regression or something similar to that is used in neural networks. So this is the foundation. Okay, what is that 1 over 1 plus e to the negative z? What does that mean? When I say negative z, that's our, you can just remember that's our beta sub naught plus beta sub 1, x sub 1, plus beta sub 2, x sub 2, plus beta, all the way up to beta sub n, x sub n. So that's what the z represents. What is 1 over 1 plus e to the negative z? This is something special in math called the sigmoid function. This formula is called the sigmoid function. And what the sigmoid function does is it takes that output of z, whatever that evaluates to z, and it maps that to a value between 0 and 1. You can try it. Try it on your calculator. Try it on some math website on your computer. Try 1 over 1 plus e to the negative and put any number in there and see what the output is. You will find that it's always, it maps any real valued number to a value between 0 and 1. You'll find that it constrains it to some decimal point between 0 and 1. So that's what we have here. And it's represented as this, you'll see it sometimes called the S-curve here. And that's how we get these models to interpret probability. So essentially, if you have a value of -6, it gets interpreted as almost 0. If we have a value of -4, that function maps that to maybe slightly more than 0. If you put in -2 for that z value, it'll map it to, I don't know, maybe like 0.2. If you put in 0, if you put 1 over 1 plus e to the -0, you get 0.5. If we put in 2, that'll map it to maybe 0.8 or so. If you put in 4, that'll map it to almost 1.
Is this the same function that even if we were to go beyond plus or minus 6, that it would never give you a value of 0 or 1? It just constantly gives you more decimals.
Oh, that's it. Is this a limit here?
Yeah.
Is it approach the limit?
Or if we were to do -7, would it go beyond? I was just curious because that's what I had in my head.
I believe you're correct there. I believe it approaches 0, but never actually reaches 0. And it approaches that limit, and it approaches 1, but never actually reaches 1. I can confirm, though. That's a good question. All right, so I think how are we feeling about this conceptually? You guys wondering maybe how does this actually work within a problem? How do we actually apply this to a data set? Let's look at the probability of passing an exam versus how many hours you spent studying on an exam. And here we have each black dot represents a student here. And maybe there's some students who spent less than an hour studying on the exam. And here in that sigmoid function on this blue line in the middle, we're representing the probability of pass-fail. And let's just say our 0.5. Let's say if it's greater than 0.5, if it's greater than 0.5, we're going to give them we're going to say they passed. We're going to use 0.5 as our threshold. And we're going to say if it's less than 0.5, we're going to say they failed. That was the outcome. And that's the outcome that the model is going to predict. But in reality, we have students up here. Let me just start at the bottom. So down here on the bottom, we have all the students that have failed the exam. So every black dot on the bottom, when I say the bottom, I mean down here. I'm not sure if you guys can see my cursor or not. So down here, these are all the students that have actually failed. And we see some students spent less than an hour, some students spent between 1 and 2, and there's even some students who spent more than 3 hours studying, 3.5 hours studying, and they failed. These students up here passed the exam. And we see some students, a lot of these students studied quite a bit. So some of these students studied more than 4 hours. But some of these students, this one particularly studied actually less than 2 hours. And these people studied somewhere between 2 and 4. So what we did is we fit a sigmoid function here. And this model will make predictions. And we can ask it, look, if a student studies for 1 hour, what is the probability that they're going to pass the exam? And we can map it to this line here. And maybe that's like point like 1 or something. So they have a 0.1 probability of passing the exam. Since 0.1 is less than 0.5, we predict that they're going to fail. Okay? Equals F. That's our prediction. And in reality, they did fail. Now let's talk about a piece that's maybe more contentious. Let's look at the middle here. What if a student studies for 3 hours? What is the probability that they are going to pass the exam? Well, let's follow this up to the blue line, and it's like right here, so 0.55. And since 0.55 is greater than 0.5, we're going to say that the probability that they pass, or the probability that they pass is 0.55, and we're going to predict that they pass. But in reality, we see that this person studied for 3 hours. This person studied for more than 3 hours. And this person studied for 2.5 hours, yet they all failed. So again, all models are wrong. Some are useful. It was not correct in these instances. In this instance, it was correct. They studied for more than 3 hours, and they did in fact pass. So the point I want to make out here is there is some overlap here between these outcomes where these probabilities will be wrong. Of course, these probabilities are correct. And of course, here we are. These probabilities are correct, or they map 100% to these outcomes. But in this middle section here, there is some ambiguity. And what logistic regression enables us to do is to use our data to map that ambiguity to some degree and measure of certainty. So this is logistic regression applied to a real world problem. I'm going to pause here for a second. In this case, we have one attribute, which is the hours studied. So in our y equals mx plus b, our y equals beta sub naught plus beta sub 1 times x, we just have one beta sub 1. Beta sub 0 is our intercept. That always exists. But our beta sub 1 times our feature, that one feature is hours studied. And our y target variable, what we're trying to predict here, is are they going to pass or are they going to fail? Obviously, more features would probably make it easier for us to make this a higher quality prediction, but this is easy to visualize in 2D. Any questions so far? Okay. Is there anything confusing about this? All right, we'll keep working through examples. Pause me if there is. One thing that we can do with this, in this example, I set something called our threshold at this 0.5. I said, yep, if what our model is going to do is it's going to calculate these probabilities first, and then it's going to look at those probabilities, and if they're above 0.5, it's going to say pass, and if it's below 0.5, it's going to say fail. We can change that. So if we found that that did not make sense for this problem and that we had higher performance by putting the threshold at a different location, then we can do that. And this is what a threshold is. We can change something called the decision boundary here. So we have these outcomes in our model, and when X is this value, it's mapping that to a probability of 0.3. And when X is this value, it's mapping that to a probability of 0.8. And we're saying anything above a threshold of 0.5 is yes in terms of outcomes. Everything below a probability of 0.5 is no in terms of outcomes. We can change that. We can, maybe you work for a company and you want them to have a very conservative model. And you only want them to classify as yes if the probability is very, very, very high. If your model is really certain and very confident and it's a really high likelihood that that outcome would occur, in that case, we can move the probability threshold all the way up to 0.8. We can say only classify people as this outcome if your probability is greater than 0.8. And if you're less than 0.8, classify it as this other outcome. So changing what I really need here is an interactive visual that you guys can like slide this threshold level and see how this model gets things incorrect or correct. But changing the threshold changes the performance of your model. It'll change which situations your model got correct and which situations your model got wrong. So in this case, we moved our threshold. Remember I said you can move your threshold up. We moved our threshold all the way to 0.9. We set our decision boundary at 0.9. So that means we're only classifying as yes for whatever our use case is if it's greater than 0.9 probability. So in this case, look, we got all these check marks right. We said, is this spam? And only do it if you're above 0.9. And it got all of these check marks correct. But there were a couple of check marks here that actually map to probabilities below 0.9 based on our features. So let's see, this one maps here, this one maps here, this one maps here, oops, this one maps here. So these are the situations in which we were wrong. We incorrectly classified these positive instances as a negative instance. So the answer was actually yes, those are spam. But in these situations, we said not spam. We said no spam. Okay, SPM, because I'm really slow at writing. In these situations, the blue box is where we said, our model said, yes, spam. But it wasn't always correct when it said yes. It was correct a lot of the time. It was correct on all these check marks. But this situation here, it was actually wrong. This one, in fact, was not spam, but our model said it was yes. So this is something called a false positive. We falsely said that it was spam. This is it for decision boundaries. Before I move on to the cost function, any questions about this so far?
I have one. It seems to me that there's a kind of a sub question here that's like false positive versus false negative, like the ethics of that and like how you. I'm thinking about like courts, right? So like we use innocent until proven guilty as a sort of a weight that we place toward being innocent because we would prefer that. Is there a way to sort of speak to that maybe when you're deciding this, or even just saying like we've chosen a model that eliminates false positives and false negatives because you can retest with a false negative, and then if you pass again then you probably be fine or something like that. I don't know.
Absolutely. No, that's a really salient question. And the short answer is yes. You can control, you can put metrics that reward or penalize your model based on it performing against false positives or false negatives in particular ways. And we're going to learn about that a lot in the metrics course. And the emphasis, the two terms I would look up are precision and recall. And then the score that we're going to learn about in that course is something called the F1 score, which can be generalized into something called the F beta score. And the F beta score can be programmed really to emphasize either precision or emphasize recall. So I have a really particular example of this. I worked for a company that had contract documents, and these contract documents would receive comments on them. And a series of 9 different teams might need to take action on a given contract based on the comments. So we trained a model, logistic regression model, for each of these teams that said, does legal need to take action on this contract? Does sales need to take action on this contract based on a comment made on it? Does HR need to take action on this contract based on a comment? And they actually preferred that there are 2 outcomes. You can either over-notify people and make sure that you catch everything, that every single person was notified that always needed to be notified, but you're probably sending extra notifications in order to get that level of performance. So you can either emphasize recall, which is over notify people, and then maybe every legal gets notified a bunch when they actually didn't need to, and it maybe wastes their time a little bit. Or we could focus on precision, and we could focus on only notify someone if you are really, really, really sure that they need to be notified. The downside of that is to get really good at precision, the trade-off you're going to make is you're going to miss notifying someone when maybe you should have. The model wasn't quite as certain, and so there were maybe some comments they should have taken action on, but they didn't. In the case, what the stakeholders wanted in that use case was to be over-notified. So we created an F1 score that rewarded the model and selected the best model that would essentially over-notify someone and notify as many teams as possible as it thought needed to take action on that. So in that case, we were controlling we were rewarding the model for having fewer false negatives, and we were controlling for, and we were going to have more false positives as an outcome of that. So you can kind of use metrics to control that lever. Threshold is another thing that it's related to that. The threshold here, as you move the threshold up, I believe you're going to have higher precision. I'd have to think about this. I think you're going to have higher precision, and you're going to have fewer false positives as you move this threshold up. So they're kind of related to each other. Did that answer your question?
Yeah.
Okay, great.
Or good enough for now, anyways. I'm sure there's a lot more there, and it's very complicated. So
Yeah, always happy to talk more. That's a great question. Okay, this formula is very important. And I know it looks scary and it looks meaty and there's a lot of numbers on the slide, but I actually think it's a super clever formula, and it's a little easier to talk about when you guys are all here and we can whiteboard. So I might try to whiteboard it. I'm just really slow on the screen here, but let's talk about this. So in logistic regression, there is a cost function based on the maximum likelihood estimation function for linear regression. And this is how the model finds the best parameters. So one, question you might ask is, great, we've got all these parameters in that 1/1 plus e to the negative z formula. How does the model actually find the best parameter, the best parameters. And it is this cost function called log loss. And the reason I say log loss is really important is because it's a very foundational metric to neural networks. And today, a really important output from neural networks is something called log probabilities, log probs. And this is the foundation to that. So this is very relevant knowledge that you can apply to output from large language models, from LLMs. You can apply this to log probs. So let's break it down, because it looks really meaty, but really what's happening here is it's a switch function. And sometimes it turns on and sometimes it turns off. So let's break it down. Hold on, let me get my pen. There we are. I'm going to try to write on the slide. All right, so let's look at just the interior piece of this formula. We know that, we know that 1 over n just means average, right? And we know that this is a summation function. So we're just saying, perform this calculation for everybody in our data set, and then take the average value of that. And from the output of this, we're going to get a negative. So we need to negate the negative. So let's negate that. Okay. So really, all of this is just averaging. This just says, take the average and negate it. So the average of what is now the question. So we can ignore, for the purposes of understanding the formula, the entire first half of this. Great. Let's set all that aside. Now we have y at I times the log of y hat at I plus 1 minus y at I times the log of 1 minus y hat at I. Okay, let's try to map this to an actual problem. So we have y at I. Let me just see if I can do this. Y at I represents what was the ground truth answer? Was it 1 or 0? So let's say I need to make a table here. Let's see, we have y at I. I'm not even going to say y at I. Well, it's already on there. So we have y, which is our ground truth. That's our y true, or our y test. And then we have, what did our model predict? So we have y hat. So there's a couple different scenarios that can happen. And y hat's a probability. So we either, let's do this, 1, 1, 0, 0. And let's do 0.8, 0.2. This really does lean better towards a whiteboard, 0.8 and 0.2, okay? What we're saying here, what does this mean? In this first row, y is 1 and y hat is 0.1. That means in reality, the answer was yes, it was spam. And our model said, I'm pretty sure it's spam. It was very confident. So this is a confidently correct answer. This first one is confidently correct. I can't write that down because it would take too long to write. Just remember that. The second answer here is when the ground truth answer was 1 and our model said 0.2. This is a confidently incorrect answer. So not confidently. This is a very, very far incorrect answer. So our model said 0.2. It said, I'm very sure that this is of class 0. And it turns out it was of class 1. And that's really bad, right? In this case, in the first one, we were off by 0.2. We were 0.2 units of probability away from being correct, of the correct answer of 1. In the second one, we were off by 0.8. That's really bad. That's not good. So this is a really bad situation. All right, let's look at this next one. The answer was 0, and we predicted 0.8. That's also really bad. We want our probability to be close to the answer. So we were off by 0.8. The answer was no, this is not spam. And we said 0.8. I'm super confident this is spam. I would classify this as 1. Remember, anything above 0.5 is spam. Remember, anything below 0.5 is not. Okay, in this final one, we said 0.2 and the answer was 0. That's pretty good. So keep in mind that this is a good situation, this is a good situation, and these are bad situations. Let's math this out. All right, so y at I, we said the y at I was 1. Let me just write the formula here. Ooh, this is gonna take a while. Y at I log. Do you guys think if I whiteboard, you'd be able to see it?
If you roll the whiteboard closer to the computer, perhaps.
All right, we're gonna try this. I'll write this formula out. I'll finish this. I already started. And we'll do one example on the slide because I will save these annotated slides and send them to you guys. The other 3 I'm gonna do on the whiteboard because this is quite painful, probably for both of us. Oh man, let's see, I'm trying to log. All right. I'm going to need you guys to run my log calculations for me. So get up your Wolfram Alpha or whatever. And by the way, it's a log, I believe it's log base 2, not log base 10. So, all right, so y, let's just plug and play. This is a plug and play formula. We have our answers. We have y is 1, and we're going to take the log of y hat, which is 0.8. Somebody tell me what the log of 0.8 is. Log base 2, I believe. Oh, sorry. All right.
You said log of 0.8?
0.8.
You want the whole number?
What did it give you? What's the first 3?
No, I'm way off probably. I got negative 0.096910013.
Perfect. 0.09.
Yeah, 69.
All right. So here is what's interesting about this formula. We had, let me see if I can get the laser pointer. There we are. So we had y time, remember in this formula, we have y at I times the log of y hat at I. So y at I times the log of y hat at I. Y at I, the ground truth was 1. So we have 1 times the log of 0.8 because our y hat was 0.8. So 1 times anything is itself. So essentially, what this is saying, this is the clever part. I'm trying to get a different color. Oh, that's not a different color. Sorry. When y at I is 1, then we just take the log of y hat. When y at I is 1, we take the log of y hat because look what happens with the rest of the formula. So we have plus 1 minus y at I times the log of 1 minus y hat. 1 minus 1 is what? That's not a trick question.
0, my bad.
1 minus 1 is 0, and 0 times anything is 0. So remember I said this function is a switch function? When y at I is equal to 1, we take the log of y hat, and this goes to 0. So the second half of the equation goes to 0. You don't even have to worry about it. You just take the log of 0.8. Now,
That is cool.
Yeah, isn't it cool? For you math nerds there, this is pretty neat. Now, when y at I is 0 in these other two instances, we turn on the other half of the equation, and we take the log of of 1 minus y hat. And you might ask, so you are really, I know it looks like a meaty equation, but in reality, you're only looking at one half of the equation or the other half of the equation based on whether you predict the ground truth was 1 or the ground truth was 0. And the ground truth is always
Why
0.
why was there a 0.2 at the second log at the end?
Oh, I was trying to
Oh.
fill in this where I did 1 minus 1 is the log of 1 minus 1.
Okay.
I should have
1
done
minus 1 minus 0.8 is 2. My bad.
No, you got it. That's exactly correct. 1 minus 0.8 is 2. So at the end of the day, our log probability for this one record, for this one here, is negative 0.09. Remember, I said there's this negative sign in the beginning that will negate the negatives at the end. So really, it's 0.09. So what does that mean? That's a really low log probability. So, or I'm sorry, that's a really low, that's a really low log probability. So we're trying to minimize this value. So that's good. That's a small amount of error. We were very close. Let's try to whiteboard these other, I'm going to roll the whiteboard closer and we're going to switch the view. So I'll rewrite some of this stuff. Let's see. What do we think? All right, you guys can kind of see that, right? We're going to erase this stuff. Okay, time check too. Let's see. All right. This part is important, so I don't want to rush us through it. So we have this whole function where we're saying y is equal to negative 1 over n, and we have the sum of, I'm going to try to remember this, and somebody call me out where I'm wrong. I'm going to skip all the i's and indices. I'm just trying to try to simplify this. So we have y times, I need to look at the slides. Yeah, y times log of y hat plus 1 minus y times the log of 1 minus y hat. All right, so, and we had this chart that we built out, and we said we have y, this is our ground truth. This is what happened in reality. It was spam or it wasn't spam, so it's either 1 or it's 0. And then we mapped it out across a couple different situations with our y hat in terms of what did our model predict. And it either predicted 0.8 or 0.2, in this case 0.8 and 0.2. And we said, 1 to 0.8, that's pretty good. That's pretty close. 0 to 0.2, that's pretty close. These two, it's pretty bad. So this one, our log prob outcome here was like 0.09. Okay, loss. I'm going to call this loss. Our loss here was like 0.09. Okay, let's apply it to this other one, this 1 and this 1 and 2. And remember, 1 minus 1 is 0. This part gets thrown away, so we're not even going to look at that half of the equation. We're just going to look at this. So if y true is 1, let's look at y log of y hat. So here we have, and really we don't even have to do y log of y hat, it's just log of y hat because y is 1, right? 1 times anything is 1. So let's just look at log of y hat. In this case, can somebody take me to the log base 2 of 0.2?
Negative 0.6989.
Right, 6989. And again, the negative gets negated at the end of this whole function, so we don't have to worry about that. So 0.6, 0.70. Whoa, that's way different. 0.09, 0.70. That's a way worse loss. That's not good. So this is showing that this formula heavily penalizes confidently wrong predictions. So let's look at the other situation when this is 0. I'm going to write out this whole formula again applied to the 0 so you guys can see that the function negates itself. So y times our ground truth is 0, our probability is 0.8. So I'm just going to plug and play y into here. So we're going to have 0 times the log, our probability is 0.8, plus 1 minus 0 times the log 1 minus 0.8. 0 times anything is 0, so this goes away. 1 minus 0 is 1, so this is essentially 1 times the log of 1 minus 0.8. The 1 times anything is itself, so this is essentially the log of 0.2, which we already know the log of 0.2 because we calculated that. So this is 0.70. And we can skip this half of the equations because now we know if y true is 0, then we're going to do log of 1 minus y hat. We're going to do 1 minus y hat because 1 minus 0 is 1, 1 times itself. So if y true is 0, it's log of y minus 1 hat. If y true is 1, it's log of y. So I can simplify this equation to 2 lines. It's a lot, but it's really simple. It's 1 minus y hat. We know that in the case of this one, y hat is 0.2. So we know that the log of 1 minus 0.2 is 0.8. So the log of 0.8 here is 0.09 because we already calculated that for this. So I want you to notice that this is 0.2 away from 1, and this is 0.2 away from 0. So why do we do 1 minus y hat? Because we want to account for when it is 0, how close is it to 0? When it is 1, how close is it to 1? So that's why we have this on-off switch function. If we just always took the log of 0.8 and treated that the same, whether it was 1 or 0, if you predict 0.8 and the answer is 1, we want to reward you. But if you predict 0.8 and the answer is 0, we want to penalize you. So that's why we do the 1 minus. The 1 minus is for the situations when it's 0, we're subtracting how far away from was it from that actual ground truth prediction. Okay, I'm going to pause. What do you guys think about that?
Simple, a little bit simpler than linear regression.
A little simpler than linear regression. All right.
It was easier to follow, at least.
Absolutely.
We will do more whiteboards. I feel like it's the whiteboard that helped with that one. Okay. Maybe I'll do office hours here sometime and do a whiteboard session. Okay. Only moving this so I can sit down. Good. That's a cost function. I probably went a little too far into that because we definitely talk about that in the metrics class, so we'll talk about that more. But I think it's helpful context for you guys to have, and it'll serve you well, certainly, especially with large language models and AI. You guys will be really able to understand those outputs, which is cool. Here's a compare and contrast for linear regression and logistic regression. I think this is our last slide. I'm looking at evaluation metrics for linear logistic regression and limitations. Okay, yeah, this is pretty much our last slide before we have a couple summary slides. A couple of key differences. If you guys are thinking, okay, logistic regression, linear regression, how do I know when to use one? What's the differences between these? Here's a straightforward summary. In linear
Emily,
regression, oh, yeah.
screen.
Oh, thank you. I'm looking sideways and you guys are looking at the side of my face. That's not great. Here we are. And thank you. I'll give you guys a second to consume this. In linear regression, we are working with continuous variables. So the target variable that we are trying to predict, not continuous variables in terms of the feature, but the target variable we're trying to predict is a continuous variable. When we're looking at logistic regression, the target variable we're trying to predict is either 0 or 1. It was spam or it wasn't spam. You guys saw from the formula, those are 0 or 1 ground truth outcomes. And logistic regression gives us probabilities that we can map to those outcomes. Linear regression is used for regression tasks, and this part is maybe confusing because regression's in the name, but logistic regression is used for classification. Logistic regression is not used for regression. It's just called logistic regression because it uses a linear regression in that sigmoid transformation formula. So if we look at linear regression here, for example, if we have our problem that we were talking about, either this is spam or this isn't spam, or this student, did they pass the exam or did they not pass the exam? The downside with trying to apply linear regression to that type of formula, let's try to fit a best fit line to this type of data, is that we can exceed that. So if we get a 2 for is this student going to pass the exam or not pass the exam, what do we do with a 2? What do we do with a -1? So in this case, a sigmoid transformation where we can map these this X variable, maybe this is time studied, to actual probabilities is more useful for us. Okay, are there questions on the difference between linear regression, logistic regression? All right, I know it says breakout, but I'm going to go through these last 2 slides. I think I have 2. Oh, summaries, and then we talk. And okay, that's just additional content. I put some additional content on thresholds here at the end, if you guys are curious. But I think we actually talked quite a bit about those thresholds and decision boundaries. I think that's pretty covered pretty well. In the next course, we're going to, I know we already talked a little bit about precision and recall, but we're going to focus more on precision and recall. So one question you might have is, okay, we have a logistic regression model. How do we know when it's doing well and how well it's doing? And this is a question I asked you to think about in your homework assignment. I said, how would you theorize, how would you suggest that we evaluate the performance of this model? And here are some metrics we can use to do that. We can use accuracy. Everybody's really familiar with accuracy. How many times were we correct? Over how many instances did we make a prediction? We can look at true positives, true negatives, false positives, false negatives. We can use those in a metric called an F1 score, which is the harmonic mean between precision and recall. Precision being the proportion of positive predictions that were actually positive, recall being the proportion of actual positives that were correctly predicted. So recall being, of all the situations that were spam, did we catch them all? You don't have to worry about this for this course or for the exam or anything, so don't stress about these metrics. Next course, but I wanted to bring that awareness to you guys so you can start mapping that in your mind. A few limitations to be aware of with logistic regression. Because it's based on that linear regression formula, we are assuming a linear relationship between input features and the log odds of the outcome. I think there are some problems that are really complicated. For example, the seats in a car, number of seats in a car, and the price of a car are not linearly related in some situations. So usually, you know, a 2-seater car is kind of cheap, and then maybe we get a 4-seater car and it's like a little more expensive. And then you get those fancy cars that have like the extra row in the back, and you know, those are maybe like even more expensive. But it's not necessarily linear, because then we get into sports cars, and those are also 2 seats, but they're also really expensive. So you get kind of this curve that's a nonlinear relationship between price of a car and number of seats in a car. And so that violates the assumption of linearity of this input feature and the outcome. So there are other algorithms that we're going to talk about that are not constrained to that linear limitation. And those are things like random forest, for example, is a nonlinear algorithm. So we're going to explore that. I'm going to provide those for you. But just so you know, when we talk about linear regression or logistic regression, they're always constrained to that relationship. That leads to the second bullet on the slide, where it says it's not suitable for complex nonlinear data. It's because of what I just described. So when you have data that doesn't have linear relationships, and decisions are modeled in a more complex way, things like random forests or neural networks, which is actually can be seen as maybe a series of logistic regressions combined together, can actually solve that better. The other thing to be aware of, just like linear regression, because logistic regression is just a transformation on linear regression, sensitive to outliers. If we have a house whose house price is way over here compared to the other houses, that can skew our model's determination of the coefficients, and then can essentially skew the performance of the model. So it doesn't do great with outliers. It can really bias the model's decisions. So you may want to handle outliers before you put them into your model. If you want it to perform well on the bulk of the data, the general situation, and not perform well on the outliers. So it's a powerful tool, predicts probabilities. I would lock that away and keep that with you. And the decision boundary piece is very important, that we can change the threshold for output determination to classify these outcomes. Model inputs are mapped to probabilities using our sigmoid function. And the cost function for logistic regression is log loss. All right, any questions? I'm going to keep these annotations and I'll add that to our slides. If not, I'm going to stop the recording, and I really did want to get to the discussion question today. So what is your stance and thoughts on the use of AI education, particularly in grade school education? I'm thinking about pre-college, essentially. So let me just stop the recording here. And I will stop share too.